All right, here we are. All right, so I know I've missed the past couple of days. Christmas Eve and Christmas, that kind of took a lot out of me, preparations and all that other stuff. So let's kind of get back to some things. So let me just review real quick. I think it was here. I'll just grab this guy. And let's make sure that we remember how to graph, right? So for example, if I have f of x is equal to, let's say, x minus 2 squared minus 5. And there I go again, forgetting that I've got my face in a bad spot. That's okay. Quick adjustment, and now we can see. All right. So when we see an expression like this, and we're supposed to graph this, we want to make sure we understand what the basic shape is. And because we have the square, that tells me that I'm dealing with a parabola. Okay, so it's going to be something like this. Okay, cool beans. And now we need to figure out what the other numbers mean. So when we have a number inside the function, so this is inside the square, this means that we are going to shift horizontally, but the opposite of what we see. So even though I see a minus 2, that means I'm actually going to move to the right 2 units. And I've got this minus 5 that's out here, and this minus 5 is outside the square. The square is not affecting that guy. So we do exactly what we see there, and we move vertically. So that means here we're going to go down 5 units. So we go ahead and start with that, and that's going to be our vertex. So right 2 and down 5, so we're going to do that guy right there. And as soon as I've done that, I can go ahead and check those guys off. I've done that, no need to worry about anything else for that part. And then from this new vertex, we're going to build our quadratic. I think you're okay, Missy. So we'll see how things go today. I've got both of my, not both, all 3 of my dogs in here. And so let's see if they will behave while I stream. All right. So because we have the squaring function, we're going to mark this off so it's 0, 1, 2, and 3 relative to that new vertex. Excuse me. All right, so I've got my vertex in place. I don't need to worry about plugging numbers and getting a brand new value, a new set of t-tables. Use the fact that we have a squaring function and build from here. So 1 squared is up 1 from that new horizontal. 2 squared is going to be up 4 units. 3 squared is going to be up 9 units, like that. And because we know that we have symmetry with a parabola, with a quadratic function, we can copy these points on the other side, just like that. And then the rest of this is a matter of connecting the dots to form a nice parabolic shape. So it's going to look something kind of like this. Now, I think I mentioned this before, but let me go ahead and say it again. For the parabola, for any of these polynomial functions, when you get to the ends here, when we get to the far left and right sides, these guys are going to continue to go up and up and up. They're never going to flare out like a flower or anything like that. All right, and so that's it. That's all we have to worry about doing for graphing that. Now, if I were to go on and ask extra questions here and say, what's the domain? Well, since we're dealing with a polynomial function, the domain is going to be all real numbers. Always and forever for a polynomial function, it's all real numbers. For the range, remember the range is going to be the set of y values, so we have going from bottom to top. And the lowest that we have here is going to be a y value of -5. It's going to have a bracket because we are including that. And we go all the way up toward infinity. So there's the range. Now some other pieces of information that I might ask about this. And I know that they kind of do this in the homework. Let's go and do this here. Finding the intervals over which your function is increasing or decreasing. So remember, we talked about increasing and decreasing as we move from left to right. Now, as I graph this guy and you trace along, it's going to be going down. It hits that vertex, and it's going to curve and go up. So as you go from left to right, you are decreasing on the values of x from negative infinity up to positive 2. So imagine that we have this. If I kind of highlight this part right here, this is where your graph, as you go from left to right, is going down. And then once you get to positive 2 and you go beyond, that's where the graph starts to curve and go up. So in terms of the intervals of the domain, he's increasing on, parentheses, positive 2 to infinity. That's how we do it. So hopefully that makes sense with what I'm doing there. Again, not trying to confuse anything here. What I do want you to notice is that we're not having to plug in a bunch of numbers. We're not having to do a bunch of arithmetic. We do need to understand how a squaring function moves and how it operates. And we also need to know how the numbers inside and outside of the function will determine a shift, horizontally or vertically. So once I go to the right 2 and down 5, this is where I'm going to start there, and then I build from there, pretending that that's like a new origin. And so the biggest math I have to worry about is doing 3 squared, which is just 9, which should not be a huge stretch at all for us. What? Whoa! Oh, what did you do? Oh, okay. Well, that is kind of annoying. Okay. Now, if I were to do this, if I say f of x is equal to negative 2 times the square root of x plus 3, and let's say plus 4. So all the stuff that's going on here, the first thing we want to focus on is the fact that we have a square root. And because we have a square root, we know the shape that we're working with. So that shape is the guy who starts here at the origin, and he goes up, and he curves out to the side, like a half sideways parabola. Okay? This negative that's in front means that we will reflect across the x-axis. That means what typically we would say is like it turns it upside down. Okay. The 2, so let me do this. So this 2 indicates it indicates a stretch by a factor of 2. So all of the key points we would have had for the square root function we'll now take those vertical changes and multiply them by 2. So it's going to be twice as tall. The plus 3 on the inside, we do the opposite of what we see, so we'll go to the left 3. And the plus 4 that's on the outside, we're going to do exactly what we see and go up 4 units. So let's get the first point in place. So left 3 and up 4 from our origin. So left 3 and up 4 is going to be right here. So I've done that, and I've done that. And as you have seen me do many times already, I'm going to dash out a new x-axis and a new y-axis. Now, for the square root, we know that there are certain values that we want to work with. 0 is a good value to take the square root of, as is 1. And then jumping over here to 4, right? So we skip 2 and 3, we want to go to 4, 5, 6, 7, 8, and then 9, because these are your perfect squares. Now, if I did not have the 2 in front of this, and just had the negative, then you would have key points following the pattern for the square root function. So the square root of 1 would be 1 but going down, the square root of 4 would be down 2, and the square root of 9 would be down 3. So without the 2 stretching it, you'd have a graph that looks kind of like that. So now let's apply that stretch of 2. It's going to take this change here of 1, and it's going to double that. So it's going to be down 2 units. This would have been down 2. You double that, so you're going to be down 4 units. And this, because the square root of 9 is 3, that's the change you have there, and we're going to double that, and we're going to be down a total of 6 units, like that. So it's basically the same shape, but we're just taking it and we are stretching it out a little bit. And now we draw a nice, smooth curve through those points. Something to watch out for when it comes to the square root is that as it's curving and going down, it's going to continue to get lower and lower. Now, it's not going to go like make a sharp turn going down. It's also not going to curve up. We're going to be careful about that. If I were to talk about the domain is, again, the set of x values that we use here. And we have a restriction based off of that radical, really the radicand. The x plus 3 has to give you something that is greater than or equal to 0. So if you thought about that off to the side and you said, okay, I know that x plus 3 has to be greater than or equal to 0, you move the 3 to the other side and you see that x has to be greater than or equal to negative 3. That's your domain. So in interval notation, that's going to be from negative 3 going to the right toward infinity. Now, of course, we can see that from the picture, but I'm just also wanting you to see algebraically how we arrive at that. For the range, the normal range for the square root function would be from 0 to infinity. Well, having a negative in front turns that upside down, so it would be from negative infinity up to 0. And then we take all of that and we shifted it up 4. Again, you can see that here in the picture. So my range, as I go from least to greatest, bottom to top, it's from negative infinity, and then it hits a maximum value when y equals 4. So there you go. Hopefully it should be, and it should feel as simple as that. Now, while we're doing graphing here, I'm going to go ahead and touch on something that will be like in a section or two after this. But again, we're talking about graphing, so let's go ahead and do that. So this next part, we're talking about rational functions. And these are functions that are fractions, for lack of better words, right? So let's talk about your reciprocal function. The reciprocal function looks like this. F of x is equal to 1 over x. So if you remember a few days ago, I said that for most of these functions that we come across, the domain should be all real numbers. But then there are two things we're going to see right now that will limit your domain. One of those being the square root, which we saw back over here. The other thing is when you have variables in the denominator. Because if you have variable expression in the denominator, that means that there's this potential that that denominator could become 0, which will make the entire expression undefined. And we don't want to do that. So knowing that we have x in the denominator here tells me that I might have a restriction on my domain. Now, before we jump into that, let's come up with a t-table of values so that we can try to get an idea about the shape of everything. So let's plug in -2, -1. I'm even going to plug in a fraction -1/2, and you're going to see why here in just a moment. And then 0, 1/2, 1, and 2. All right. So the reciprocal function does exactly what the name suggests. It takes any input value and it spits out the reciprocal. In other words, it takes the fraction and it turns it over. So if I plug in -2, flipping that over, I get -1/2. Plug in -1, and the reciprocal of that is -1. If I plug in -1/2, and I flip that guy over, that gives me -2. Now if I try to plug in 0, well, we have a bit of an issue, because you'd end up with 1 over 0, and as we said before, you're not allowed to divide by 0. It gives you an undefined expression. So right now we see that we're going to run into a bit of an issue here with the domain. It's not all real numbers. Looks like it's going to be everything but 0. Leave it. Just lay down, girl. Here. Lay down. Stay out of trouble. Dogs, am I right? You be a good girl and you lay down. No, you don't need to do that. You're just trying to get in trouble, aren't you? All right, let's look at the positive ones. I plug in 1/2, the reciprocal is 2, reciprocal of 1 is 1, and the reciprocal of 2 is 1/2. Now, what you're going to find out here with the reciprocal function is that the bigger the number, the smaller the output value. And the smaller the input value, the larger the output value is. Will you just stop that? You girls don't need to be biting at each other. Leave it. All right, so let's plot these points and see what we have. All right, so we have -2 is -1/2, -1 is -1, and this -1/2 is going to put me down here at -2. And then on the other side, we have 1/2, which gives me 2, 1 gives me 1, and 2 gives me 1/2. So you'll see that if I keep going out here to the right, if I plugged in 3, I would have 1/3. Plug in 4, I would have 1/4, and so on. These values are going to get smaller and smaller and get closer and closer to 0, but you won't ever be able to actually touch 0. No matter how big of a number you plug in here, 1 divided by a number is never going to be 0. Now, it might be close enough to where you would say it's practically 0, but it never actually equals 0. Excuse me. Stop it. Stop it. All right. And then as I get closer to x, this guy's going to get larger and larger. Closer to 0, excuse me. He's going to get larger and larger, but he's never going to be able to actually touch that y-axis because that would be x0, and it makes the expression undefined. And we have a similar shape down here in quadrant 3. It's like we took whatever was there in quadrant 1, and we rotated it 180 degrees, and now we have this shape. All right, so this is the basic shape for your reciprocal function. Now, some things to notice here is that we're going to have this kind of imaginary vertical line right here, and this is your vertical asymptote. All right. Let's make sure that we spell that correctly and that we say it correctly. It's asymptote. It's not asymptote. It's a T-E there at the end. And so this vertical asymptote is the equation x equals 0. And so any vertical asymptote, that means your function can never cross that. It's acting as kind of like a force field. The closer you get to it, you're going to have to curve away one way or the other. And this reciprocal function isn't the only guy that has a vertical asymptote. We're going to see some more of those next week. Now you also have a horizontal asymptote, and that's going to be this guy right here, which happens to be along the x-axis. So the horizontal asymptote, and that's going to be the equation y equals 0. Now, the thing about the horizontal asymptote, it's not necessarily a force field or a little barrier like the vertical asymptote is. In fact, you can cross the horizontal asymptote. What it's there for is that it's there to describe the end behavior that we can see with these, well, right now, these rational functions, but other functions later on. So as x goes out toward positive or negative infinity, it tells you what your graph is starting to behave like. And so for this one, it's saying that as you go out toward positive or negative infinity, your graph starts to get closer and closer to a y value of 0. Now, there are some graphs that we're going to see where this horizontal asymptote only describes one side of that end behavior, not both sides. Yeah. All right, so let's talk about the domain and the range here. So as you can see in the picture, the domain is not everything. The domain is going to be everything but 0. So we would express that by saying from negative infinity to 0 parentheses, union 0 to infinity. And you'll see that the range is going to be exactly the same thing. For the y values, we're using everything except y equals 0. And so my range is going to be from negative infinity to 0, union 0 to infinity. Now, there becomes this kind of difficult aspect of this when we start talking about where is this guy increasing or decreasing. I hope it's pretty clear to see that when we look at the basic graph, this guy is not increasing anywhere. On the left side, he's going down, and then once you cross that vertical asymptote, he's still going down. So if I ask you where is he increasing, you would say he's increasing nowhere. But what about where is he decreasing? And this is where things get kind of tricky, especially when you're doing something, when you're answering a question like in My Math Lab or some of those other online courses. So some people might say it's decreasing everywhere, but we've got to be a little bit careful about how we say that. What we will say is that it's decreasing on the interval from negative infinity to 0. That is one complete interval where it is decreasing, comma, and then it's decreasing again from 0 to infinity. We can't actually put a union sign in between that. Oh, thanks for the love, P-Pound. And the reason we can't put a union symbol is because when we talk about where are we increasing and decreasing, we have to think about one interval at a time. So it's decreasing when I go from negative infinity to 0. Set that aside. And then it's decreasing again from 0 to infinity. So, and the reason I point this out, especially if you are my students, you'll see this question come up in the homework, and it's going to ask you, over what interval or intervals of the domain is your function increasing or decreasing? And if you look carefully, it'll say use a comma to separate your answers as needed. So you have to make sure that you do the comma here and not union, because each interval that I have written there is a solution for where is it decreasing. Compare that to when we talk about the domain, where we say the domain is all of this, and we use the union symbol right here. So for the domain and range, we're just talking about a collection of those x or y values that we're using for the domain or the range respectively. So for the domain, we're using all of these guys joined with all of these guys over here. So they're taken all together collectively. All right. So that is your basic reciprocal function. Now let's look at someone who is also kind of in this section. And this is going to be the reciprocal squaring function. And again, they're kind of on the nose whenever they name these functions. The reciprocal squaring function, excuse me for going too fast there, is f of x equals 1 over x squared. So not only are we having to do the reciprocal, but we also have to square as well. Okay, so I want you to think about what that looks like in terms of our t-table. Now, I know that there's the square there, but we have to avoid the temptation of saying, oh, it's just going to be a parabola. And it's not, though. It does have some similarities with the parabola in terms of symmetry, but that's kind of it. Oh, appreciate that, Very. So I want to use the same input values that we use for the reciprocal function up above. So we can see how some things are similar, but a lot of things are different. So when it comes to coming up with these key values, you've got two things you've got to do. You have to do the reciprocal, and you've got to square. Now, fortunately for us, the order in which we do these doesn't really matter. So if I look at x equals -2, suppose I want to square first, and then do the reciprocal. All right, so if I square -2, that's +4, and then I flip that over, and I end up with 1/4. Now see, for that one, it's a little bit easier to do that as opposed to flipping and then squaring. But again, that's just me. Now if I do -1, -1 squared is +1. If I flip over +1, I end up with just 1. All right, well, that's kind of the same as the reciprocal function. Now -1/2. I suggest that you think about flipping before you square. Because if I flip the -1/2, I get -2. And the -2 squared is +4. And then we get to 0. And just like it was for the reciprocal function, for the reciprocal squaring function, it's going to be undefined. So whether you well, here's the thing. If you squared 0 first, you get 0. Great. But you do 1 over 0, it's undefined. And if you do 1 over 0 first, well, that's undefined. And what is undefined squared? Well, it's nonsensical, right? Now, if I go to 1/2, you're going to see that we end up with a positive 4, and then we have 1, and then we have 1/4. So you're going to see here some symmetry on either side of your y-axis, which is super nice for us. So when I plot these guys, let's see, we've got -2 and positive 1/4, -1, 1, 1/2 is positive 4. And again, because we have that symmetry, just copy these guys on the other side of the y-axis just like that. Oh, wait, I'll get to the questions here in just a second. All right, so now that we do these, we connect the dots here. Let me scroll up a little bit because I do want to make sure I graph to the edge of my graphing window. And so you're going to see it has some very similar tendencies that we had from the reciprocal function. As I get closer to this y-axis, he's going to blow up one way or the other. And as I go out toward positive or negative infinity, he starts to flatten out. So, whoops, that is not what I meant to do. All right, so we have my vertical asymptote, and you'll see me abbreviate this just by saying VA. And this is the equation x equals 0. And then we have our horizontal asymptote of y equals 0. It's true that asymptotes never meet y and x. Wait, what? So peak bound, I'm not sure about your comment there. I don't know if you're asking if it's true that asymptotes never meet the y and x axis. These guys are like the base asymptotes for your parent functions are the axes themselves. But the asymptotes would, I mean, they're lines, right? And what we know about lines is that they go forever and ever in both directions, right? So even once we go off of this grid, they're still going on. And especially when we're looking at this in behavior, as I go out here to the right, the distance between the graph and the asymptote is going to get smaller and smaller and smaller as your function gets closer and closer to that asymptote. So let's quickly toss up here my domain and range. So the domain, it's just like it was for the reciprocal function. It's everything but 0. Now your range is a little bit different because your range has nothing that's negative. Everything here is positive. So it's coming from 0 and it goes up toward infinity. And we use parentheses on the 0 because we're never going to have a point on this graph that has a y-coordinate of 0. It never actually touches the x-axis. You're okay. Now, let's talk about where are we increasing and decreasing. Because you'll see here that as I come from the left, this guy is getting bigger and bigger, and then he hits that vertical asymptote wall, right? He just goes right up along that. So he's increasing on the left side, so increasing from negative infinity to 0. But then once you get past that vertical asymptote and you trace, you're going down from left to right. So then you're decreasing on the interval from 0 to infinity. And ta-da, that's it. So the key thing here is understanding what are the key, what's the basic shape, what does the parent function look like, and what are the key values. Because, excuse me, once you get that, we add that to our library of functions. So if I want to grab that guy and shift him up, down, left, or right, it shouldn't be a problem, right? So if I were to do this, if I say f of x is equal to 1 over x plus 5 plus 2. So we don't see a square root, we don't see a square, we don't see absolute values, any of the things that we've seen before. But we do have x in the denominator. And it notice that it's just x. You don't have x squared. You don't have parentheses squared. So this should have the basic shape of our reciprocal function that has the curve in the lower left and in the upper right. All right. But what did the plus 5 and the plus 2 do? Well, they do the same thing they've been doing this whole time. The plus 5 is in the denominator of the fraction, so he's in the main function part here. So that means we have a horizontal shift opposite of what I see. So we're going to move to the left 5. Then you get the plus 2 here, which is completely outside of the fraction. So it's a vertical shift, and you go up 2. We haven't flipped this guy over. We haven't stretched or compressed this, so it's going to be our normal shape. Now, here's where we run into a bit of an issue. Back over here, like the first example that we did today, the right 2 and down 5 gave me that vertex. And so I plotted the vertex, and then I graphed from there. But here, the left 5 and up 2 isn't going to give me a vertex. It's not even going to give me a point that's on the graph, because the origin wasn't a point for the parent function, but we can use that as a reference point. So even though we don't have a vertex or a key point like we had for the square root function, we can still shift some things around, mainly those asymptotes. So the main vertical asymptote was at x equals 0. Now take that guy and move it to the left 5 units. So to the left 5 units, just like this. All right, so I have my vertical asymptote x equals negative 5, hence left 5. And then I have my vertical asymptote, which is going to be, it was y equals 0, but we're taking all of that and moving it up 2 units. So up 2 units just like this. So my horizontal asymptote is y equals 2. Remember, all of your vertical lines are going to be x equals a number. All the horizontal lines are y equals a number. So I'm not putting a point here. I'm just highlighting that this is where your origin would have been. And from here, we're going to plot those key points from our reciprocal function, which would have said that the reciprocal of 1 is 1. The reciprocal of 2 is 1/2. And if I did 1/2, the reciprocal is going to be 2. Take those guys and rotate them 180 degrees about that new origin. So you would have like the -2 and the -1. So you have -1/2, -1, and then at the halfway mark, you would have a -2. Take these dots and do your best. You don't get a whole lot of points here because it's kind of hard to plot those fraction points. But we do know that as I go out here to the right, I'm going to get closer and closer to that horizontal asymptote. I shouldn't be touching it, but of course I know that when we're doing things by hand, there might be a bit of an error where you might accidentally touch that. But as long as you're not like going underneath it or you're not going down and then bouncing up, I think we're going to be okay. Again, graphing is one of those things. It's just like drawing any like art thing. You just have to keep working at it. You got to practice, right? You can't just say, oh, I did poorly and then give up. No, you go back at it and do it again. And so there you go. Again, nothing, to me, I don't think anything too crazy about this. But I'm also the kind of guy who wants to ask you, what's the domain? What's the range? Where are you increasing? Where are you decreasing? Now, I would also ask for the asymptotes, but I already have them labeled here and here, so I don't need to really ask for that again. All right, your domain. Your domain would have been everything but 0, but we shifted everything to the left 5 units. And so now it's everything but -5. So -5 is now the value of x that causes my denominator to be 0. So I have to eliminate him. Almost makes me sound like I'm a hitman. Ooh, I'm a mathematical hitman. No, that's going to lead to all kinds of weird complications. The range would have been everything bottom to top except y equals 0. But now we see it's everything from bottom to top except y equals 2. So that's -∞ to +2, parentheses, then union, 2 to infinity. Done. Where are you increasing? Well, as I trace along from left to right, I'm going down, and then I'm going down again. So I'm increasing nowhere, and I'm decreasing in 2 different spots, kind of like what we talked about a while ago. You're decreasing from negative infinity to negative 5 from those x values, right? And then you have another region where you were decreasing, and that's when the x's go from negative 5 to positive infinity. Meaning, as your x values get bigger, your y values get smaller. That's what it means to be decreasing. So hopefully that's not too bad, right? Now, let me show you the kind of question that I might like to put on a test. Because if we understand how the +5 and the up and the +2 mean horizontal and vertical shift, it doesn't matter how big these numbers are. So suppose I say, suppose I do this. I say f of x is equal to the square root of 7 over x, let's say plus 200 squared, and then minus, I don't know, let's say 68 pi. Now, I definitely would not ask you to graph this on a graphing grid. This is going to be messy. It's going to be ugly. I don't care about that. But here's what I would care about. I would ask you for the domain, the range, horizontal asymptote, vertical asymptote, where are you increasing, and where are you decreasing? And I don't want to hear things like, oh, these numbers are so big. Who cares? Do you understand the concept? Because if you understand the concept, the numbers don't really mean anything. I mean, whether I write 6 or 68 or 68 pi, still just a number. And the way that it will react with your main function is going to be the same. So first, let's talk about what's going on here. Let's talk about our shape. Your shape is going to be coming from the fact that you have parentheses squared and it's in the denominator. So it means we're talking about this basic shape right here, your reciprocal squaring function. We're taking that guy. All right, and what are we doing with it? Well, we're going to be shifting it, right? What does this mean on the inside? Because see, this is inside the function because it's inside the square. This means that I'm going to the left 200 units. Could have been 2,000 for all I care, but I just wrote 200, right? This minus 68 pi is outside of the fraction, it's outside of the square, and this tells me my vertical shift is going to be down 68 pi units. Now, what we do not want to do is we don't want to try to convert that into some kind of decimal. That's not going to be helpful at all, and it won't be exact. Okay, what about that square root of 7? This square root of 7 would give us a vertical stretch by a factor of the square root of 7. But what we'll find out is that a vertical stretch or compression is not going to affect my domain or range or any of this other stuff. It'll affect the way the picture looks, but it doesn't affect the information that I'm asking for. All right, so let's just draw a quick sketch. We know that we should have a horizontal asymptote and a vertical asymptote, and my graph should look something like this, right? The only way it would look different than this little volcano shape is if I had a negative in front, which would just turn that upside down. But I don't have the negative in front, so it should be something that looks kind of like this. Now, please understand, I'm not going for accuracy here. I'm going for understanding the concept. This is what my shape should look like. Now, to find my domain and range, it's good for me to find my asymptotes. So, saying that I go down 68 pi tells me something about my horizontal asymptote. It was y equals 0, but I took that and I went down, so minus 68 pi. That is your horizontal asymptote. Your vertical asymptote, it was x equals 0, but what did I do with my graph? I shifted everything to the left 200 units. So that's going to put this at x equals negative 200. All right, so let's write that down. Horizontal asymptote, x equals negative 200. Vertical asymptote, y equals negative 68 pi. Let's find the domain. Excuse me, something stuck in my throat, I guess. The domain. The domain should be everything except what makes the denominator 0. And I think it's pretty clear because we've got that vertical asymptote at x equals negative 200 that our domain is going to be everything except for negative 200. So from negative infinity to negative 200, union negative 200 to infinity. And what about my range? My range going from bottom to top starts at y equals negative 68 pi, really just above that. So parentheses, negative 68 pi, and going all the way up toward infinity. There's nothing below it. And now increasing and decreasing. As I go from left to right, we see that on the left half here, I am going up, so I'm increasing on that open interval from negative infinity to negative 200. Because remember, we're talking about parts of the domain where our y values are going up as my x values are going up. And then we have where we're decreasing, and that's going to be on this other half here from negative 200 to infinity. So as x increases over there, y is going down. That means it's decreasing. All right, so even though I have crazy numbers, who cares? If I'd made this, 68 pi squared, that means we're going down 68 pi squared units. So my vertical asymptote is y equals negative 68 pi squared. So then my range is negative 68 pi squared to infinity. And there's my how I make those changes, right? It's just a number. And again, don't try to give it as a decimal, because if you give it as a decimal, it's no longer going to be exact. And we want to be exact as long as possible and not have to worry about a decimal until at the very, very end. All right, now let's get on to some, what I think is some fun stuff. That's one of my, not sure if it's my favorite section to teach, but some of my favorite problems to do. And that is working with synthetic division. So synthetic division is kind of a shortcut way of doing division with polynomials. But what we're going to be looking at here is when we're taking something that is essentially f of x and dividing it by something of the form x minus k. And then what do we get out of that? So we end up with a quotient plus a remainder over x minus k, which is the divisor. Okay, so let's make sure we remember these keywords. So this is the divisor, and this guy right here is the quotient. So whenever we're doing this division, these values that we get, these expressions, these functions, are going to be unique. It's the same thing that we ran into whenever we have an improper fraction in just basic arithmetic. So if I take, let's say, 45 divided by 7. Now, 7 doesn't go into 45 evenly, and you might even go up to the side here and say, okay, well, let me just do the math. 7 going into 45. 7 goes in 6 times. You do 6 times 7, you get 42, and subtract that. So you get 6 with a remainder of 3. When we did this back in the day, we would have written this as a mixed number. 6, and then we take the remainder over the divisor. Okay? Now, when you say 6 and 3/7, that's the same thing as saying 6 plus 3 over 7. Exactly the same thing, right? And that's what we're going to be doing now, but with polynomials and other crazier looking functions, okay? The thing that you have to make sure you know how to do is how to add, subtract, multiply, and divide. That's all I'm asking of you. And also being neat. I don't think that's too much to ask. All right. So the key thing here is to identify this k value. Now notice that this says x minus k. So when I'm trying to identify the k value, I have to do the opposite of what I see there. So let me just run through an example of how synthetic division works. And then we'll go on to some more complicated things and some really neat problems that we can do. So for example, if we were tasked with dividing 2x squared plus 5x plus 1 divided by x plus 4. Now, we could do this the long way when it comes to dividing polynomials. In fact, I'll probably do that here in just a second. But let me show you how synthetic division works. Now, this is supposed to be of the form x minus k. So because we've got that minus there, even though I see a plus 4, my k value is actually going to be the opposite of that, negative 4. All right, so let me show you how I set things up. Now, this may be different from what you've seen before or what your particular textbook shows you. This is the way that I learned it, and this is the way I keep doing it. Now, for this little box that you have, you need to make sure that you have enough room inside here for 2 rows of numbers. Okay? You don't need to create like a huge amount of space, just enough so you can clearly write your 2 rows of numbers. And I'm going to put some headings here. I'm going to put my k on the top here. Now what I'm dividing into, my dividend, goes all the way up to the 2nd degree. So I'm going to make sure I have a place for x squared, a place for x, and then here at the end, my constant. And then what we do is that we populate this with the values that we're given. The k value is going to be the opposite of what I see there with a plus 4. So I'm going to write a minus 4 here. And then I'm just going to write these coefficients now. So we'll have 2x squared, 5x, and plus 1. All right, that's it. The rest of this is a matter of adding and multiplying, just going back and forth. The first thing we do, though, is that we will immediately bring down this lead coefficient of 2 down here to this bottom. And this is where we're going to end up with our answer. All the stuff that's in there that I have highlighted as blue is this like scratch work type stuff. So what I'm going to do is that every time I've got a number down here, I'm going to multiply it times the k value. So negative 4 times 2 is negative 8, and that goes up here. And now in that column, I'm going to add those guys. So 5 minus 8 is negative 3. And then I multiply times that k value again. Negative 4 times negative 3 gives me positive 12. 1 plus 12 is 13. Now here I'm going to put a little box around that because that's going to be a special number. And that special number is our remainder. So you see above the top there that I have those headings x squared, x, and the constant. When it gets to my answer, everything gets reduced by 1 degree. So this is going to be the coefficient for x, 3 is going to be my constant, and 13 is going to be my remainder. So that means that when I work this out and I write my answer, it's 2x, again we see that down here, 2x, minus 3, and then I'm going to do plus. We do a fraction bar. Sorry, again, my face is in the way. Do a fraction bar, and then we do the remainder, which is 13 over the divisor x plus 4. That's the division. So synthetic division can be very, very quick. You don't have to worry about your powers or writing your variable. It's all a matter of multiplying and adding and just going back and forth with that until you get to the end. Now, let me show you what would have happened if we had done this the long way. The long way being, of course, long division with polynomials, where you would write x plus 4 as the divisor out here, and then dividing that into 2x squared plus 5x plus 1 for the dividend. Now, the way that the algebra works here is that we focus just on the x right now. And you think, okay, what do I multiply the x times to get 2x squared? And the answer would be 2x. And then we take that 2x just like we would with long division, and we multiply it times the divisor. 2x times x is 2x squared. 2x times 4 is plus 8x. So we see that the leading terms look exactly the same, which is what we want, because the process for long division tells me to then subtract what I have here. So that means I change these signs like that. So these guys go away. So they look the same at first, but that subtraction step that we have with division is going to make those guys go away. And now we have negative 3x plus 1. And we do the same thing. What would you multiply x times to get negative 3x? That would be a minus 3. So then we multiply. Negative 3 times x plus 4 is negative 3x, and then minus 12. Again, with the long division, you draw the line and you change these signs. So this becomes a plus, and this 12 also becomes a plus. Those leading terms go away, and I end up with a remainder of 13. And if you look, that's the same thing that I already had, right? In fact, look at these numbers that we get. This minus 8x is this minus 8 that you see right there. And when you combine the 5 and the negative 8, you got negative 3x. So there's your negative 3. And then you had this plus 12, which is that plus 12 that you added with the 1 to get 13. So it's all the same numbers, but you don't have this long drawn out process. You don't have to worry about, changing your signs here and there and worrying about how many factors of x you have and what the power is. You don't worry about any of that. Synthetic division keeps things nice and compact. So for a lot of the problems that we're going to be doing here, we're doing synthetic division, but we don't just leave at synthetic division. We then have to translate the work into the answer. For example, if I take 3x squared minus 5x plus 1, and I divide this by x minus 2. Again, I could do this the long way. I could do that long division with the polynomials that I just did, or I use synthetic division. So I'm going to set that up over here. Remember, make sure you have enough room for 2 rows of numbers in there. Up above, I'm going to write my headings. So I've got my k value, then I have x squared, x going down to my constant. What we're going to find out here is that when we're doing our headings, you can't skip degrees. So if the largest degree term you have is degree 4, you have to have a column for x to the 4th, x to the 3rd, x squared, x, and then your constant. You cannot skip things. Now, what I'm dividing by here is x minus 2. So the k value that I use is the opposite of that, which is a positive 2. And then for these coefficients, I just copy them down exactly as I see them. 3x squared minus 5x plus 1. And then there's going to be the box there for my remainder. All right. I'm going to use blue here. I like blue better. So the first thing I'm going to do is I'm going to bring the 3 down here. And now we multiply times the k value. So 3 times 2 is 6. Add these guys in the column. Negative 5 and 6 is positive 1. Multiply times k again. So 1 times 2 is 2. Add in the column, and you end up with 3. So all the stuff that you see over there is my scratch work. That's the synthetic division. So now let's take these numbers that we have from this bottom row and write them as our answer. Because this is now supposed to be the coefficient for x. This is now for my constant, and the 3 is my remainder. So writing this out, we have 3x plus 1, and then plus the remainder over the divisor. And that's our answer. Now, just like with division before, we can check our work. So let's do a quick check here to make sure that what we're doing makes sense. So to check, take your divisor, x minus 2, times my quotient, 3x plus 1, and add back in the remainder. And if I do that, that should be the same thing as my dividend, the 3x squared minus 5x plus 1. So let's take a moment, especially in a problem that's small like this, and check it just to make sure that everything is okay. So let's FOIL this. X times 3x is 3x squared. X times 1 is plus x. Then we distribute the negative 2. So negative 6x minus 2, and then there's a plus 3 that we bring down there at the end. Combining like terms, we have 3x squared minus 5x and plus 1. So everything checks out the way that it's supposed to. Perfect. Now, I do want to show you something, and this kind of connects with some other stuff we're going to be seeing a little bit later today, but it's how we can use the synthetic division to rewrite the dividend. So if I just have 3x squared minus 5x plus 1, so this guy on its own, he doesn't factor. But if I look at the work that I've done, we see how we were able to take this factor of x minus 2, and we're able to break this guy down as something times that x minus 2, and then plus this remainder. So the synthetic division would allow us to fill in the blanks here and say, oh, well, x minus 2 went in 3x plus 1 times with a remainder of 3. So let me take this and jump into something called the remainder theorem when it comes to synthetic division. Really, really love the remainder theorem. So the remainder theorem says that if f of x is a polynomial function with real coefficients, then f of k is equal to the remainder of f of x divided by x minus k. So let me try to break this down for you. This is saying that if you want to evaluate a polynomial function, and you've got the input value here of k, you could just plug that value into the function. Or you could do synthetic division using that k value, and the remainder from synthetic division is the same value as if you evaluated that function at k. So I want to use something from the very last problem so you can kind of see how it's all connected. At least I hope you'll be able to see this. So f of x is equal to 3x squared minus 5x plus 1. I could say find f of 2, right? And if I do f of 2, that means I would do 3 times 2 squared minus 5 times 2 plus 1. All right, so 2 squared is 4 times 3 is 12 minus 10 plus 1, and this equals 3. All right, so we did that the long way. But I want you to notice that this 3 that I got is the same thing as the 3 that we have there for the remainder. Now, for a polynomial that's as small as this quadratic, you could just plug it in, right? Now, I want you to see something though. So we took 3x squared minus 5x plus 1. And we were able to rewrite that, if we scroll back here just a little bit, we could rewrite that as x minus 2 times 3x plus 1, and then plus 3 out on the end there. So if I took that same expression, I mean, it's the same function, it's just written a little bit differently, and I say find f of 2. That means you plug 2 into x, and you do the math. But watch this. 2 minus 2 is 0. So it doesn't even matter what happens with this stuff over here, because 2 minus 2 is 0, so this guy's all going to become 0, and you're just left with 3. So hopefully that example there can show you why it works the way that it does. Because if we get that, then we can evaluate some really nasty looking functions just by doing synthetic division. All right, but let's do this. Let's do another division problem to make sure we understand how to do synthetic division anyway. All right, you know what? That looks like a good jump. So we've got x to the 6th minus 15x to the 4th minus 7x to the 3rd plus 50x plus 17 all divided by x minus 4. Now, you might see me kind of glancing over here to the side because I do have some problems already written down, because synthetic division, it's not the kind of concept where I'm just going to make these guys up off the top of my head. That's where I can get into a lot of trouble. All right, so synthetic division, let's get this set up here. Got my little box. I'm going to put my k value out here, and we see that we go all the way up to x to the 6th. All right, so I have to have a heading for x to the 6th, x to the 5th, 4, 3, 2, 1, and then my constant. I can't leave out anybody. So I'm dividing by x minus 4. Oh, sorry, girl. I'm dividing by x minus 4, so my k value is going to be positive 4. I do the opposite of what I see there. I have 1x to the 6th. Then I have minus 15x to the 4th. So that minus 15 goes under x to the 4th. This is why I want you to put your headings there so you put the coefficients in the right spot. You might say, well, what about the x to the 5th? Can I just erase that? No. We don't see x to the 5th here, which means he's understood to have a coefficient of 0. And that is important. It's like a placeholder in a number. If I write the number 207, well, of course, I always forget about my face. So if I write 207, is it important for me to write the 0 between the 2 and the 7? Yes, because that is the placeholder for my tens. And you can't just ignore that because you don't have any tens. You still have to put that there. It does mean something. Same thing's going to be true if I have a coefficient of 0. I need to have that there. All right, then I have minus 7x to the 3rd plus 50x. So I jump all the way over here, which means I have another 0 for x squared. My constant is 17. And then I'm going to be trying to find what that remainder is. Well, not that it's asking me for the remainder, but just making sure I kind of separate that off to the side there. All right, first things first is we just bring down the coefficient, leading coefficient, just as we see it. That's a 1. Sometimes I get going too fast, and I multiply it times the k value when I shouldn't. You don't multiply it times k until this next step. So 1 times 4 is 4. Add these guys and I get 4. Multiply. 4 times 4 is 16. Add and I get 1. Do it again. 1 times 4 is 4. Add and I get negative 3. Multiply times 4, I get negative 12. So I add to get negative 12. Let's make sure I'm not making any careless mistakes because that happens to me way too often. All right, multiply times 4 is negative 48. Add, I get 2. Multiply times 4, and I get 8. And so my remainder here is 25. So again, this is my work. But let's make sure we answer the question. The question here says divide. So we're going to take all of this work and we're going to write our answer. So that first column started out as x to the 6th. But at the bottom, when we look at our quotient and we analyze this, that's going to be the coefficient for my x to the 5th term. So it's going to be 1x to the 5th plus 4x to the 4th plus 1x to the 3rd minus 3x squared minus 12x plus 2 plus, do your remainder piece. Your remainder is 25 over your divisor. Now your divisor is not 4. Your divisor is x minus 4. So there is our answer. Again, we've got to make sure that we take our time step by step, piece by piece, until we can get to the very end. And then we translate our work into the answer. In this case, it said to divide. We divided. We have, excuse me, we have the quotient, and then the remainder over the divisor. All right, so let me show you one that a lot of my students freak out about when they see this in the homework. All right. All right, so I'm going to take x to the 4th plus 2/3 x to the 3rd minus 7/9 x squared plus 5/27 x minus 14 over 81. All divided by x minus 2/3. Excuse me a moment. Let's see if you can set this up and kind of get started on the synthetic division process. You know what? I'll give you a bit of a hint. Start with that. All right, so the thing to watch out for here, I mean, we can say fractions, but we don't need to be so concerned about it because remember, fractions are just numbers. My k value is going to go out here, and I see that I go all the way up to x to the 4th, so let's make sure that we have representation all the way down. All right, so my k value, I see a minus 2/3, so my k value will be the opposite of that, so positive 2/3. I have 1x to the 4th, 2/3 x to the 3rd, minus 7/9 x squared, plus 5/27 x, and then minus 14 over 81. All right, first thing first is to bring down the 1. Times the k value, so that's going to be 2/3. So I mean, it's just really 1 times 2/3, right? And then when you add these guys, they already have a common denominator. So 2/3 and 2/3 is 4/3. Please remember that when you are adding fractions, you have to have the same denominators. And then you just add the numerators. You don't ever add denominators. All right, multiply times 2/3. So if you're kind of shaky about this, think about what you're doing here off to the side. 2/3 times 4/3. When it comes to multiplication, we just multiply straight across. 4 times 2 is 8. 3 times 3 is 9. So up here we have 8/9. These guys have the same denominator, which is great. So we combine these and we get a positive 1/9. Now times the k value again. 2 times 1 is 2. 3 times 9 is 27. Oh, sweet. Another common denominator. That's awfully nice. So 7/27. One last time. So we have 2/3 times 7/27. 2 times 7 is 14, and 3 times 27 is 81. So we have a positive 14/81. So when you combine these guys, you have a remainder of 0. That's kind of cool. It goes in evenly. So then my answer to this, so it was x to the 4th for that first column. This is now the coefficient for x to the 3rd. Then we have plus 4/3 x squared plus 1/9 x plus 7/27. Again, as long as we remember that we're dealing with just numbers, then we're going to be fine. All right, and now let me jump into doing something that uses that remainder theorem. All right, yeah, let's do this. Suppose we have f of x is equal to x to the 5th minus 2x to the 4th minus 29x to the 3rd plus 27x squared plus 39. And then I ask you to find or evaluate f of 6. Now, you could do this the long way and just replace all of the x's by 6 and do the math. I really don't want to do that, though. I mean, yeah, I know what 5 to the, or what 6 to the 5th is, what 7,776, but maybe you didn't know that, okay? What we can do is use synthetic division, because if I do synthetic division with that value there for k, then the value that I get for my remainder is the same value as f of x. All right, so let's set up synthetic division. And it's going to be especially true here that this synthetic division is just my work. It's not my answer. Again, do your headings. K, we go all the way up to x to the 5th, so make sure that we have a column for every degree decreasing by 1 until we end up at the constant here at the end. And here at the very end, that remainder is where our answer is going to be. All right, so here's the thing about using synthetic division and the remainder theorem. The k value here, since there is no like x plus or minus like we had before, so like over here, when I needed to identify my k value, this guy right here, even though it says minus 2/3, I used a positive 2/3. So when you have x plus or minus, do the opposite of what you see. But when you're doing the remainder theorem, and they ask you f of 6, that value is your k value. No need to change the signs. Like, not saying there's no need, just don't change the signs. Use that for your k. So it's going to be 6, and then we have 1x to the 5th, minus 2x to the 4th, minus 29 here, 27. 39 is my constant, so he goes here, so I skipped my x term, so I have to put a 0 there. All right. Go through the same process that we've been doing. Bring down the 1 times the k value of 6, and now we add, we get 4. Multiply times k is 24. sorry, wrong color, is 24. There we go. Add, we get negative 5. Multiply is negative 30. Add, we get negative 3. Multiply is negative 18. Add is negative 18. Multiply 6 times. Did I make a mistake here somewhere? Something doesn't feel right. Hold on a second. All right. So 6 times negative 108. No, 6 times 18, excuse me, is negative 108. Don't know where my mind was. Sorry about that. And then 39 minus 108 would be negative 69. Yeah. All right, so that's my scratch work. But now my answer. My answer is f of 6 equals negative 69. And so I like doing this a lot better than actually plugging the number into the function, because I noticed like the largest number I had to contend with was at the very end, 6 times 18 to get 108, and then combining that with the 39. If I just plugged 6 into all those x values, again, I'm going to have some really large numbers. Like even doing 6 to the 4th, I mean, it's 1,296, but maybe you don't know that number. If you don't have a calculator, it's really going to be not a lot of fun. All right, well, let's try what looks good. All right. You are okay. There's no need to be grumpy or any of that stuff. Yeah, okay, let's do this. If I say f of x is 3x to the 6th minus 40x to the 5th plus 50x to the 4th minus 20x to the 3rd, you know we're having fun now. Whoops. Minus 48x squared plus 7x plus 103. Barely fits. And then we want to evaluate f of 12. Yeah, so I definitely do not know what 12 to the 6th is, and I really don't want to have to work that out on my own. Yeah, really don't want to look at that. But I do have synthetic division. And with synthetic division, this is my k value. So let's set that up and see how nicely synthetic division works. So I got my k value here, and I go all the way up to x to the 6th. So make sure that we don't skip anybody as we work our way down to get to my constant term. So 6, 5, 4, 3, 2, 1 constant. Okay. The k value is just as I see it, the 12. And then we got the 3, negative 40, 50, negative 20, negative 48, 7, 103. I'm pretty sure if I remember this problem correctly, this was one that I made up with my students as I was trying to get them to understand that when I make these problems, I kind of build it as I go along. I'm not putting numbers and hoping that it works out. I have control over the values that I use, so I make sure the numbers work out nicely. So I tell them that if the numbers like get really out of control, like really, really big, that they've probably done something wrong. All right, so starting first with the 3. So bring the 3 down to the outside, and now it's all about multiplying and adding. 3 times 12 is positive 36. We add to get negative 4. Multiply to get negative 48. So when I was doing this in class, we would have had negative 48, and I was saying, okay, what would be a good number to kind of help balance out the negative 48 so that the numbers aren't growing? And so you want something that's almost like the opposite of negative 48, but maybe off by a few numbers. So if I put a positive 48, it would have given me a 0. But a positive 50 gives me a nice manageable 2. We can handle 2 times 12, right? 2 times 12 is 24. Negative 20 and positive 24 is 4. Times 4, or times 12 again, is 48. So now this gives me a 0. 12 times 0 is, of course, 0. 7 and 0 is 7. 7 times 12 is 84. So here at the end, we have an answer of 187. So evaluate f of 12. F of 12 is 187. And that's it. The synthetic division was there to provide the work, but it wasn't the answer. We had to peel off from that guy what the actual answer was, which was evaluating f of 12 equaling 187. So you see that we didn't really have a lot of large numbers to deal with until the very, very last step. I don't even know if I would consider 84 a large number. But it's a whole lot easier than actually replacing all of the x's with 12. At least, that's what I think. All right. Now some fun stuff. Still using synthetic division. We want to talk about zeros of polynomial functions. All right. So let's start here. If I say that x equals k is a 0, sometimes we'll call it a root of a function, what are some things we get from this? Well, if x equals k is a 0, that means that x minus k is a factor of the function. It means that f of k equals 0, hence it being a 0 or a root. And it means that k comma 0 is an x-intercept for your function if k is a real number. So there's that little conditional statement there, if k is a real number, because it is possible for us to have zeros or roots of functions that are complex or imaginary, just like we would have seen last week when we were solving quadratic equations. Okay. Another thing here, so if f of k equals 0, that means that the remainder of f of x over x minus k is 0. So if something is a 0, that means we're going to get a remainder that is 0, which is kind of cool. So a lot of times when we do division, we're hoping to get a remainder of 0. Now, you don't often get that. But if I give you a problem and I say, hey, this particular thing here is a factor. If I tell you that a number is a factor of another number, that means it can divide into it evenly. So let me take, let's do this. So if f of x equals x to the third plus x squared minus 28x minus 40, and I tell you that x plus 5 is a factor, then the kind of thing that I would say is to find all zeros and all intercepts. Now, back in the day, and by back in the day I mean last week, when we were finding all of the solutions for things, it was typically things that were x squared. And if it was x squared, we knew that we had a way of solving that, whether that was square root property, factoring, completing the square, or the quadratic formula. But when it's x to the third, things can get kind of dicey. Now we could try to look at that and say, okay, well, can I factor by grouping? Well, it doesn't always work, and especially doesn't work here. Because this is a polynomial of degree 3, I'm expecting to have 3 solutions. But I don't have enough information, or I can't take the cubic and plug it into a formula. Here's what I can do. I can use this information right here. If I tell you that x plus 5 is a factor, then that's, of these 3 solutions, I'm telling you what one of these guys is. I'm saying that we should be able to take my function and write this as x plus 5 times something else. And if we can completely factor that and there's no like extra number on the outside, then we're going to be okay. So we have a degree 3. We expect there to be 3 solutions. Life doesn't get easy until I'm down to something that's quadratic. So by knowing a factor, I can do synthetic division, and it's going to turn this from degree 3 into degree 2, and life is going to be easy for me. So let's do that. Get my synthetic division set up. Get my headings, so that's k, x to the third, x squared, x, and my constant. Now, since I'm saying that x plus 5 is a factor, that means that for my remainder, I better have 0. If I don't have 0, then something's wrong. That means either you made a mistake or I made a mistake when I created the problem and I typed it up. All right, so since I'm telling you that we have x plus 5, when I identify the k value, it's going to be the opposite of what I see, so I'll use a negative 5 here. The coefficients, I've got 1x to the third, 1x squared, negative 28x, and negative 40. All right, same as it ever was. Bring the 1 down. And now it's all about multiplying and adding. So 1 times negative 5, negative 5. We add to get negative 4, multiply to get positive 20, add to get negative 8, multiply to get positive 40, and there's my remainder of 0. Good, that's what I was supposed to have. So in terms of listing my zeros, this first one is the one that was given to us, which is negative 5. We have 2 more zeros to find because this is a polynomial of degree 3. Now, in terms of x-intercepts, because negative 5 is a real number, one of my x-intercepts is going to be negative 5, 0. I have the potential to have 2 more x-intercepts. Now, that is only going to happen if my other zeros are real. If they're not real, then I only have the 1 x-intercept. All right, so let's try to figure that out. Let's take the quotient here and write this as an equation. So that's x squared minus 4x minus 8 equals 0. We have something that's quadratic, so we know that we can solve that. So let's solve this. Let's solve this efficiently, right? Can I use the square root property? No, because I have x squared and I have x. How about factoring? Well, the leading coefficient is 1, so that's okay. But are there factors of 8 that give me 4? And the answer is no. What about completing the square? The lead coefficient is 1, which is good, and the middle coefficient is even. Even better. So let's do that. So to complete the square, we will first move the 8 to the other side. And we're going to figure out how this is going to factor and then fill in the gap here. So to fill this in, let's start with the factorization. Half of negative 4 is negative 2, and negative 2 squared is a plus 4. And I have to add that to both sides of my equation. So x minus 2 quantity squared equals 12. And now, this is the big part about completing the square, is that we can use the square root property. So take the square root of both sides. Don't forget the plus or minus. We have x minus 2 equals plus or minus. Make sure that you simplify your radical. 12 can be broken down as 4 times 3, and the square root of 4 is 2. All right, so we end up with plus or minus 2 square roots of 3. So move the 2 over so we get 2 plus or minus 2 square roots of 3. Excuse me. Maybe not. Nope. So these are my two other zeros. So let's go ahead and write them up here. So we have 2 plus or minus 2 square roots of 3. Now, since these are real values, oh, that is not where I meant to put that. Sorry, what would have been up here was the x squared minus 4x minus 8. The zeros. So that's 2 plus or minus 2 square roots of 3. Because these guys are real, they give us the following x-intercepts. So 2 plus 2 square roots of 3 comma 0, and 2 minus 2 square roots of 3 comma 0. All right, but notice that the question here said find all intercepts. Not just the x-intercepts, but also the y-intercept as well. For every polynomial function, there will be a y-intercept. It's always going to be of the form 0, comma something. If you go back to the original function, if I were to plug 0 into everything, that goes away, and that goes away, leaving us with the value of negative 40. All right, so that's how we'd go about finding all of the zeros for this polynomial function. So give you a couple of pieces of information, or in this case just one, and we take that and we just finish the rest of it. All right, let's do one more. This might be the last one today. So f of x is equal to x to the fourth plus 9x to the third plus 21x squared minus 21x minus 130. And you are given that x minus 2 x minus 2 and x plus 5 are factors. So find all zeros and all intercepts. Excuse me. All right, so notice here that we have a polynomial of degree 4. So we were expecting to have 4 zeros. So if I were to just kind of start with this, we already know 2 of those zeros because they gave us factors. So x minus 2 means that x equals positive 2 as one factor. And then from x plus 5, we would have negative 5. And then we would have 2 more zeros to find. All right, so that's what we know right now. For our intercepts, let's see if we know anything about our x-intercepts right now. Well, 2 and negative 5 are both real, so each one of those gives me an x-intercept. So that would be 2, 0, and negative 5, 0. Now, I don't know if I had 2 more. It all comes down to whether those 2 remaining zeros are real or imaginary. So, who knows what's going to be the rest of this? Now, the y-intercept, we can go ahead and find that. So it's going to be 0, comma, negative 130. Because if you plug 0 in for all those x's, the only thing that's going to be left is the negative 130 there at the end. All right. All right, so now what we're going to do is we're going to use synthetic division. So this is a polynomial of degree 4. If I do synthetic division with the first 0, 2, my quotient's going to be x to the third. And then if I take this quotient, this new guy, and I do synthetic division with negative 5, I'll be taking away another degree, and I'll be left with something that's quadratic, something that I know I can solve. All right, so let's think about how we're going to do that. All right, big synthetic division here. Make sure I get my headings, k, x to the fourth, x to the third, x squared, x, and my constant. All right, so let's use the first. It doesn't matter. First of all, it doesn't matter if you use 2 or negative 5 first. It really doesn't matter. I'm going to use 2 because it was the first thing that's given to us. Let me slide up here a little bit. My coefficients are 1, 9, 21, negative 21, and negative 130. Now, if x plus 2 really is a factor, then what I should have here for my remainder is 0. If I don't get a 0, then I've made a mistake somewhere. All right, so first bring down the 1, and then do the whole multiplication and addition back and forth. So 2 times 1 is 2. Add to get 11. Multiply, we get 22. Adding is 43. Times 2 is 86. Adding is 65. Multiplying times k one last time is a positive 130. So I do get a remainder of 0. That's what I was expecting. That's what I get. I feel pretty good. And now we're going to do the same thing on a smaller polynomial, because this was x to the fourth. It's now x to the third. So we're going to use our other k value of negative 5, and let's see what happens here. All right, so the first thing I'm going to do is bring down the 1, multiply times k. So that's negative 5, add to get 6, multiplying gives me negative 30. I see you, girl. Adding gives me 13. Multiplying gives me negative 65. So for our remainder, we get 0. Again, exactly what was supposed to happen. And now we're going to take what's left here at the very end. So it went from x to the fourth to x to the third. Now it's down to x squared. So x squared plus 6x plus 13 equals 0. And now we're going to solve this quadratic. All right, again, we go through the progression for solving a quadratic equation. Can we use the square root property? The answer is no, because I have x squared and I have x. All right, how about factoring? Are there factors of 13 that add to 6? No. How about completing the square? Yeah, because you have a lead coefficient that's 1, and you have a middle coefficient that's even. This is exactly what we want for completing the square. So, x squared plus 6x, that's going to be negative 13 when we move it to the other side. I'm expecting here this stuff to factor. So, what goes in the factorization? Half of 6 is plus 3. which means in the gap, you get 3 squared, so that's 9. We add that to the other side as well to maintain balance. Negative 13 plus 9 is negative 4. So now we can use the square root property to get rid of the square. Take the square to both sides. Don't forget the plus or minus. All right, so x plus 3 equals plus or minus. The square root of 4 is 2, and the negative inside is going to give me an I. And when you finish getting x by itself, that's negative 3 plus or minus 2i. So the negative 3 plus or minus 2i answers the question up here for your final zeros. So negative 3 plus 2i, negative 3 minus 2i. Now, since these are complex, they're imaginary zeros, they do not give us x-intercepts. So we just have these two x-intercepts. So for most of these problems, this is how it's going to work. If they tell you that something is a 0 or that something is a factor, that means that we should have a remainder of 0. And if we don't, we need to go back and see, did I copy numbers down correctly? Did I miss a sign? Did I not multiply correctly? So small little things like that, one little error is going to throw the whole thing off. However, for these problems, again, if you know that you have a factor or you have something that's a 0, then you know your remainder should be 0, so it's easy to check that. On some of these other problems here, like if I say you evaluate f of 12, there's nothing that says what kind of number you should have there for the remainder. Now, if it is a problem that I am personally creating and putting on an exam for my students, I'm going to make sure that the numbers stay tame as I go throughout the process, because I don't want to give them something that's huge and nasty and just throws everybody off. So, even though you don't necessarily know if you have the right answer, if you have something that's like in the thousands and hundreds of thousands, okay, yeah, you've made a mistake somewhere. I'm not going to do that to you. All right. Well, hopefully I'll be back again next week to do some more streams. So please like, subscribe, ring the bell for notifications and all that stuff. And hope you have yourself a